Hello, welcome everyone to this distinguished lecture series. So beginning in 2018, the Purdue Engineering Distinguished Lecture Series invites world-renowned faculty and professionals to encourage thought-provoking conversations and ideas with faculty and students regarding the grand challenges and opportunities in their fields. And besides presenting a lecture to a broad audience of faculty, graduate and undergraduate students, they will engage in an interactive panel with Purdue faculty and students. And today we have Will for us talking about quantum. But to introduce Will, I will like to invite David Barr, our Senior Associate Dean of Faculty, College of Engineering and Professor of Materials Engineering.
Don't clap for me, you're clapping for the next guy. So thank you, Premi. It's my true pleasure to introduce our speaker for today. First, just a little bit of housekeeping. It's always nice when it's really crowded. So if there's still a few chairs scattered around, so students in the back, if you are not scared of sitting next to somebody, please sneak on down. But so it's my pleasure to introduce Dr. William Oliver today for the Purdue Engineering Distinguished Lecture Series. Dr. Oliver received his PhD in electrical engineering from Stanford University, his master's in electrical engineering and computer science from MIT, and a BS in electrical engineering and a BA in Japanese from the University of Rochester in New York. He's jointly appointed the Henry Ellis Warren Professor of Electrical Engineering and Computer Science and a Professor of Physics at MIT. He serves as the director of the Center for Quantum Engineering, the associate director of the Research Laboratory of Electronics, and he's a principal investigator with the Engineering Quantum Systems Group on the MIT campus. Will's research interests include materials growth, fabrication, design, measurement of superconducting qubits, as well as development of cryogenic packaging and control electronics. From 2003 to 2023, he also worked at MIT's Lincoln Laboratory, most recently as a laboratory fellow from 2017 to 2023, where he was instrumental in growing the quantum computing group to its presence levels. He stepped down from that position to co-found Atlantic Quantum, a quantum computing startup. It was recently acquired by Google this past year. He's a fellow of the American Association of the Advancement of Science, a fellow of the American Physical Society, and a fellow of IEEE. Serves on the National Quantum Initiative Advisory Committee, the U.S. Committee for Superconducting Electronics, and is an IEEE Applied Superconductivity lead editor. So we are really excited to have him come and talk with us today about exciting things in research in all things quantum and supercomputing, and we will turn it over to Will. So.
Thank you, David.
Thank you very much.
Good afternoon. It's really a pleasure to be here. Thanks for the kind introduction, David, and for the invitation to speak with you today. I'm actually not going to talk about my own research. I want to talk more generally about quantum computing, where we've come from, where we're going, what's hard, what's likely, what's hype, and what's not. I'm actually not seeing anything on the monitor here yet. Okay, it's up. I've given this talk a few times. Well, while we're getting that going, you may recognize this picture. Usually it's in black and white. It's not in color. Oh, there it goes. Thank you. This was a Solvay conference in 1927, and as many of you know, this past year was the International Year of Quantum Science and Technology. And it celebrated 100 years of the advent of quantum mechanics. Many of the people you see here won Nobel Prizes for their work. One woman here won it twice. And we look back and we say that was quantum 1.0. That was when we first understood that nature and the world around us is fundamentally quantum mechanical. This century, we're starting a new endeavor, and it's called Quantum Information Science and Technology, and you might think of it as Quantum 2.0. And basically, Quantum 2.0 addresses the sensing, the communication, and the processing of information in ways that fundamentally use quantum mechanics to do it. And if you had to give it a definition, we would say that Quantum 2.0 does this sensing and communicating and processing in ways that are either practically prohibitive or even impossible to do with our conventional technologies. We'll talk about that in more detail, but that's a high-level definition, and I'm going to focus on computing today only, but it's broader than just computing. And to have a touch point, I like to go back and think about classical electronic computing, because we're all familiar with classical computers. Mark Twain said history doesn't repeat itself, but it often rhymes, and I find this to be quite a useful rhyming exercise. Conventional electronic computing started over 100 years ago. The vacuum tube, 3-terminal device. It was used for many years as a radio transceiver, or in radio transceivers as an amplifier. It took 4 decades, 40 years, to become used in a computer we all know called ENIAC. Now, the following year, the transistor was also invented, and this is where Quantum 1.0 becomes important, because to make the transistor, we needed to understand semiconductors, the band structure of semiconductors, and we needed quantum mechanics to do that. But once we understood how semiconductors work, we invented this device called a transistor, which is manifestly classical. It's a faucet for current. You turn the current on, you turn the current off, 0 and 1. Okay, with that transistor, about 10 years later, we had a fully transistor-based computer called TX0, invented at MIT. But it didn't look anything like what we're using today. To get closer to today's computers, we needed integrated circuits. That was the late 50s. But even with that development, it wasn't until the 70s that we started to see chips that you and I would look at and say, okay, yeah, that's an integrated circuit. Here, this one is called the Intel 4004, 4-bit processor. Another 25 years to get to the Pentium Pro. I remember using that computer, fantastic at the time. First large-scale commercial computer that had millions of transistors on a chip. And then here we are, boy, who's counting? Already 30 years later, with GPUs, CPUs, TPUs, XPUs, more than 100 billion transistors on a single chip. Fantastic technology. Took over 100 years to develop. Okay. I say that because quantum computing is much more recent and nascent compared to that. In the early 80s, people like Richard Feynman suggested that if you want to simulate quantum, use a quantum system to do that. Okay, good idea. What does that mean? It took us 15 years even to understand that. People like Peter Shor, Nishimori, Eddie Farhi, and many others, Lev Grover, developed algorithms in the 90s that told us that if and when we can build a quantum computer at scale, we'll be able to do amazing things that we simply cannot do with our conventional computers. And the last 30 years has been about trying to build those computers. And we have quantum computers today. They're just small, 100 qubits or so. But the progress is accelerating rapidly, and that's what I would like to talk about. So, takeaway message is this. Quantum computing is real. It's transitioning from laboratory curiosity to technical reality. That's happening right now. But as engineers, we know that moving from a fundamental concept to a real system is going to take time. And of course, it's going to take engineering. And the last thing is you need to be in the game. You need to be in the game to play. It's a game we want to win. But also, you think about who's making these chips today, or who's making and designing these GPUs. They didn't jump in 5 years ago once someone else figured it out. They've been in it for decades because there's so many trade secrets, so much knowledge that's aggregated in order to enable us to do that, and it will be the same for quantum computing. So with that, 2 more topics I'd like to talk about: qubits and algorithms, how they work, and then engineering quantum systems and a look ahead. So how is a quantum computer different? I like to compare and contrast against classical. So a transistor is a bit of information, a 0 or a 1. It's discrete. Transistors are almost perfect. And if we set a transistor, say, in state 1, we'll come back and measure it in state 1. Set it in state 0, we'll measure it in state 0. Quantum computers, the logic element is called a qubit, a quantum bit, and it's any coherent 2-state system, quantum coherent. We'll talk more about what that means. And the way that we think about it is in the context of the planet Earth. Now, if you're at the North Pole, you're a classical state 0. If you're at the South Pole, you're a classical state 1. Transistors live at the North and the South Pole. Qubits can be at the North and South Pole, too. Qubits can be classical. But when a qubit is anywhere other than the North or South Pole, it's in what we call a quantum superposition of 0 and 1 simultaneously. That's weird. For example, if you're standing on the equator, you're at one place. It's a single state. But you carry aspects of both 0 and 1 at the same time. This has implications. We'll go into a little more detail on it. But one implication is that measurement becomes probabilistic. And so if you stand on the equator and you measure, you will instantly snap to the North Pole with a 50% chance or snap to the South Pole with a 50% chance. Go back to the same place on the equator, and 50-50, you're going to go to the North or South Pole again. Okay, so quantum computers rely on encoding information in a fundamentally different way. One consequence of that is how we encode that information. Let's again consider a classical computer. If you have n transistors, a number n, you can actually represent an exponentially large number of states, 2 to the nth power. Let's take a simple case, n equals 3. 2 to the 3, that's 8. There are 8 ways that I can permute the zeros and ones. All zeros, all ones, everything in between. There are 8 of those. And if I wanted to use that exponentially large number of inputs to a classical computer and calculate an output, I basically have 2 ways I can do it. I can take one computer, and I can feed in one at a time, 0, 0, 0, get an output. 0, 0, 1, get an output, and do that many times. Or I could buy a large number of computers and try to do it in parallel. But either way, I have an exponentially large number of inputs. It's going to take me exponential time or exponential hardware. Now, quantum mechanically, you have n qubits, and they can represent an exponentially large 2 to the n number of classical states. But the difference is we can put all of them together into a single superposition state, all 2 to the n. And you can figuratively think about using that single input state into the computer and processing on it. Now, we haven't measured anything yet. We'll come to that in a moment. But this is intuitively why quantum computers are powerful. And they lead to something called quantum parallelism and quantum interference that I'd now like to give an intuitive look at visually. So before I do that, what is a qubit? Well, it basically comes in 2 flavors. One are the natural atoms that we get from the periodic table of elements. And depending on the number of protons, neutrons, and electrons, we know these elements will have very different properties, and some of them are useful in quantum computing, and in particular, the first 2 columns. But one feature they all have is they have discrete energy levels where the electrons can reside. And if we pick the outermost 2 shells, we can say one of those is going to be state 0 and the other will be state 1. So those are the natural atoms. We can also build superconducting circuits which mimic those properties in some ways. So depending on the number of inductors, capacitors, and something called a Josephson junction that we put together into a circuit, if we cool that circuit down to low temperatures, it will also exhibit discrete energy levels. It's a harmonic oscillator. And if we choose the lowest 2 to be our 0 and our 1, okay, we have a coherent 2-level system. And in fact, this circuit that I show here in the upper right, you could think of that as the simplest element. It's a hydrogen atom in some sense. It's our simplest electrical circuit, but you can certainly make it more complicated by adding additional circuit elements and thereby designing the properties that we want, a Mendeleev table of artificial elements. So the quantum technologies, whether computing or sensing or communication, are based on these types of 2-level systems. Okay, so let's dig into quantum interference and quantum parallelism. To do that, we need to think about quantum bits and, again, the planet Earth. So we're talking about a coherent 2-level system. Let's imagine an electron in a magnetic field, spin up and spin down, and they have different energies due to the Zeeman effect. Now, classically, I can represent state 0 as the North Pole and state 1 as the South Pole, spins pointing up or spins pointing down. Okay. But again, as we talked about, we can put these states into quantum superposition, where we're somewhere else on the planet Earth. And you can represent it in this way, in terms of phases. Should remind us of GPS, or longitude and latitude on the Earth. And one thing to keep in mind is that these are complex numbers, amplitude and phase. And so if you're on the equator, one of the phases is pi over 2, because you came down an angle 90 degrees. But then you have the whole 360 that you could describe where on the equator am I residing. So let's take 3 such spins, 3 qubits. We'll call them 1, 2, and 3. And classically, they represent 2 to the n classical states. I can write a state register of all of them pointed up, all of them pointed down, everything in between. And as we said, there are 8 of them, 2 to the 3rd power. This is just classical. But we also said that they're quantum mechanical. So I can represent all of them in a single superposition state with a weighting coefficient C1, C2 through C8. Could change it to zeros and ones if we want it to look digital. And it requires 8 complex numbers now to represent this single superposition state. And by placing those coefficients C1 through C8 in my state register, I can now make this a quantum state register. Okay, and we're going to use this quantum state register to understand parallelism and interference. So let's take it one at a time. Quantum parallelism. A typical operation in a quantum algorithm is to apply a pulse or a gate. And what we're applying here is called a pi pulse because it's going to rotate the spin 180 degrees, value pi. I'm applying it to atom 1. So if in my state register it's pointing at the north pole, this pulse is going to rotate the spin, and now it's pointed to the south pole, rotates it by pi. If the spin were at the south pole, it's going to rotate it by pi as well, and now it's going to be pointed at the north pole. That's how this works. And so when we do this, what we're going to see is that this single pulse applied to 1 qubit is going to shuttle all of the coefficients. How does it do that? Well, let's take a look at before and after. So I apply this pulse to atom 1. Let's just look at the spin up case. C1 through C4 will now become down, and the C1 through C4 coefficients follow along. The other 2 spins are exactly the same if you look at it. However, for the portion of the superposition state where the spin is down, that's going to flip up, and the coefficients follow along. So let's think about what we just did. We applied 1 pulse. We applied it to 1 qubit, and we changed 2 to the n coefficients. That's quantum parallelism. Very, very powerful. Okay. Let's now consider quantum interference. We're going to apply a pulse now to the 3rd qubit. You might notice that the amplitude is half as much. The area turns out to be half as much, and it's only going to rotate half as far. It's called a pi over 2 pulse. Before and after. And for a spin up, we're going to rotate that spin down to the equator, and I'm just going to arbitrarily call this the plus direction. Okay? Now, for the experts here, you know there's a normalization 1 over square root of 2, and I'm not going to worry about 1 over square root of 2 here just for simplicity, and it's not needed to see the interference happen. So let's just take the first one. Spin up will rotate into up plus down, and that coefficient C5 will follow along. Now, let's consider the case where we were pointed down. If we're pointed down and we rotate in the same direction, we'll be again on the equator, but on the other side of the Earth. And so I'm going to say that's a minus sign. So down goes to up minus down. And when I do that, the coefficient C6 follows along, but the minus sign follows as well. And so you could say, well, what if C5 equaled C6? Well, clearly the first one is going to double, and that's called constructive quantum interference. And the second one is going to subtract and eliminate, and that is called a destructive interference. So this is quantum interference in the context of computing. And it's also an example of quantum parallelism because it happens on the entire state space at the same time. I should say the quantum state register at the same time. So we applied 1 pulse. We applied it to 1 qubit, and all of this happened. This is what underlies the power of quantum computing. Now, these gates that we apply are actually logic gates. And we know from classical electronics, classical Boolean logic gates, I'm not going to read them all here, but there's a number of them here you'll find familiar, the NOT gate, the AND gate, the OR gate. And we know that with a combination of these gates, you don't need all of them, just a handful of them, you can do what's known as universal Boolean logic, meaning from any point in the state space, I can go to any other point in the state space, hopefully the correct answer, by applying this subset of gates. It's not unique. There are many such gates like this, or combinations of gates, but this is called a universal gate set for Boolean logic. It does require a 2-bit gate as well. Quantum computing completely rhymes with this. We have single qubit gates, which are basically rotations around the planet Earth. If I rotate around the x-axis, I'll call that an x gate. If I rotate around the y-axis, I'll call it a y gate. Z-axis is z gate, etc. And importantly, we also have 2 qubit gates. I'll show you an example in just a moment. The point is that with just a handful of these gates that I've shown, you can form a universal set of quantum logic gates. Run any quantum algorithm. In fact, you can run any Boolean logic algorithm as well, classically. But quantum computers often do no better, and usually worse than classical computers when running Boolean logic. They're actually pretty slow. But for certain problems, they vastly outperform conventional computers. Okay, so let's take a look at what a single qubit operation is. The analog is going to be the classical NOT gate. 0 becomes 1, or 1 becomes 0. In this case, our quantum NOT gate is called the X gate. It takes quantum state 0 to quantum state 1, or 1 to 0. This is what it looks like. On the left, you see our planet Earth. The blue vector starts at the North Pole and rotates to the South Pole. That represents the state of the qubit. The red vector that's coming in and out is the envelope of the pulse that I'm applying. And you can see that it's being applied to the x-axis, which is why it's an X gate. And on the right is the envelope. I'm not showing the high-frequency carrier inside, which is resonant with the qubit transition. This is just the envelope. Now, in this case, I started at the North Pole, I ended at the South Pole. Classical states. It's just a classical gate. But I don't need to start at the North and South Pole. I can start anywhere on the surface of the planet Earth, and I apply the same gate, and it's going to rotate my block vector, as we call it, the qubit state, 180 degrees around the x-axis. This is called the X gate. A 2-qubit gate, one example of the classical analog is the exclusive OR. And one way to look at exclusive OR is to say that you have a control bit and a target bit. And as you can see, when the control bit is 0, the target bit takes Y is just passed to the output. But if the control bit is 1, I'm going to invert Y. So 0 becomes 1 and 1 becomes 0. And that's the truth table for XOR. The quantum version of that is called the controlled NOT gate, as you might expect. It uses this funny symbology, but there's a control qubit and a target qubit, and it does exactly the same thing that I just described. The rotation of qubit Y is going to depend on the state of qubit X. And you can look at examples which are pretty interesting, such as this one. Here, my control qubit is in a superposition of 0 and 1, and my target qubit is solidly 0. And quantum mechanics follows the rules of linear algebra, so you can just take these one at a time. So when the control bit is 0, nothing happens to the target, and I get 0, 0. Plus, when the control bit is 1, I need to flip the Y bit so that 0 becomes a 1. And now I have a state where I can no longer factor it into something that's just X-like and something that's just Y-like. And this is called an entangled state. Of course, the experts know this doesn't prove that it's entangled. I'd have to measure it in different bases to prove that. But this is indeed an entangled state. My point here is, I won't run through anymore, but universal quantum computation is based on and achieved with a small set of these single and 2-qubit gates. And it looks a lot like conventional computing. So then what is an algorithm? Well, an algorithm is a sequence of these types of single and 2-qubit gates that gives me an answer to a problem. And the way that it works in quantum is to start with an initial state that is a superposition state of equally weighted all possibilities. And the way that I think of it is that these are possible answers to the question I'm posing, that the algorithm is solving. They're all equally weighted at the beginning. And then the challenge of the algorithm designer is to create the steps that lead to the answer. So for example, a single qubit operation. One gate on one qubit impacts all of those coefficients. There's also quantum interference, as we saw. And what happens is the coefficients, alpha, beta, gamma, delta, are no longer what they were before. They were equal. They've changed. There are also 2-qubit operations followed by quantum interference. And the goal at the end of this for the algorithm designer is to, through this interference, suppress to 0 all of the wrong answers and enhance to 1 the correct answer. That's very important. And the reason it's important is because we know in quantum mechanics when we make a measurement, the probability that we'll get any one of these states goes as the magnitude squared of that coefficient. So if the coefficient is 1, then with probability 1, I will get the answer here, it's 0, 0, 1. And every time I run the algorithm, I'll get the same thing, 0, 0, 1, 0, 0, 1. And that encodes the answer to my problem. And all of the other states, 2 to the n minus 1, I will never measure because their probability amplitudes were suppressed to 0. It's very important. Okay. So these are the quantum algorithms that we know of today, or you could say the algorithm primitives. I won't read through the whole chart, but you can see on the left the category, the algorithm type. Then the classical time is what it takes to run on a conventional computer. And the quantum time is what it would take to run on a quantum computer. Then there's a speed up and research and limitation, and all the faces you see at the bottom are my colleagues at MIT. They're not the only ones working on quantum algorithms, but I'm from MIT and I feel like I should show some of my colleagues because I don't actually work on quantum algorithms, although I should. So what are the algorithms we know about? One of the most important is quantum simulation, scientific computing, simulating or emulating another quantum system, like Richard Feynman said. Material science, quantum chemistry. Okay, this is where pharmaceutical drug development comes in. All right, and you can see that the speed up goes from something that looks like 2 to the n, exponential, to a polynomial, n to some constant. We'll talk about that in a moment. Peter Shor's algorithm is factoring. It's a number theoretic algorithm, applied mathematics. Turns out this one's pretty important. It cracks our current public key crypto systems that are in common use. That's why it's quite important. But there are several algorithms that are focused on numerical simulation. Linear systems of equations, AX equals B, pervades all of engineering. Quantum computers sample solutions to very large matrices. Optimization. Optimization is ubiquitous. Every company is trying to optimize something. And here you'll see that there's a question mark in the speed up in the quantum time because it depends a lot on what question you're asking. You know, I might use Waze or Google to find the quickest route home today, and it may not be the optimal solution, but it's a good enough solution and I'm happy with it, and conventional computers are pretty good at doing that. But if you needed the optimal solution, like your life depended on it, okay, then maybe a quantum computer has a role to play there. And then finally, search. Search is Grover's algorithm. This is a quadratic speedup. This is where it's an unsorted search of an unsorted database. So for example, if I give you a phone number, whose name does it correspond to? These things called phone books, we don't have them anymore, but we used to have them, and you would look up alphabetically ordered names, not by number. Okay, and so with that, let me now switch gears and talk a bit about engineering these systems. What is it going to take to realize commercial quantum advantage? This is very simple, but this is the way that I think about it. First off, there should be no known fast classical algorithm. If there is, use the fantastic computers we've already got. They're really, really good, and they've been optimized for more than 100 years. Second, you need to know the quantum algorithm. There has to be a quantum algorithm to solve your problem. There are many problems I'm aware of where I don't know how to do it efficiently on a conventional computer, and I also don't know how to do it on a quantum computer. Okay, so you need that. And then the third thing is it better be a useful problem if it's going to be commercial. There are many demonstrations of what are sometimes called quantum advantage or quantum supremacy, where we solve a math problem and it indeed is very efficient on the quantum computer and not so efficient on the classical computer, but there's no commercial application. And I think long-term, what we really seek is commercial quantum advantage. So the overlap of this Venn diagram is pretty small today. And I advocate to everyone here that we need to develop more quantum algorithms of the type that are useful for commercial application because we're working very hard to build quantum computers, and we want to know that they're going to be useful in the future. This is very important. Now, for such an algorithm, such as quantum simulation, there's two types of quantum advantage that we can gain, and it's represented by this simple equation here. And one is a polynomial in the size of the problem n, and the second is exponential in the size of the problem n. And what we're talking about is the size of the computer we need, the time it's going to take to get a solution, maybe the energy required to get that solution. You know, we usually think of quantum computers and think, oh, they're going to be so much faster, but it's not the only axis to consider. Now, if we improve the polynomial, this is called a polynomial improvement. Grover's algorithm is an example. It's a quadratic improvement. For example, n would go to square root of n. Okay, that's decent. It's not decent if it's 4 and it becomes 2, that's not a big deal. But if it's 1,000,000 and it becomes 1,000, okay, that's respectable. But where quantum computing really shines is on the exponential side. This is what we really seek. If you can reduce the exponential to a polynomial, 2 to the n comes downstairs and it's now in a polynomial form, that is an amazing improvement. We don't really experience exponential improvement in our daily lives. So let me give one example here of exponential growth. And if you wanted to simulate using a classical computer what's happening in a quantum computer in a brute force sense, you could ask, I've got this big superposition state. There's 2 to the n coefficients you needed to represent it. How large a memory would I need to store all of those coefficients? And if you had a quantum computer with just 30 qubits, just 30, I could probably do it on the laptop that I'm using, 2 to the 30th power number of memory elements. Don't even double it, just go to 50. Now you need a top 500 computer and the memory that's in that top 500 computer to store 2 to the 50 coefficients. Go to 80, okay, now it's getting fictitious. You need all the computers in the world networked together, leveraging all of their memory. Double that to 160, you can go to Wikipedia and find that 2 to the 160th is about all of the silicon atoms on the planet Earth, each one being used as a memory element now. And just 10x where we started, with 300 qubits, now I need all of the atoms in the known visible universe, and each atom is being used as a memory element to store the coefficients in this massive superposition state of just 300 qubits. Okay? That's exponential growth. It's mind-blowing. Of course, the challenge is to leverage it and take advantage of it, right? And that's what we're trying to do with quantum computing. Now, why don't we have quantum computers right now? It comes down to 2 time scales. One is called the coherence time, and this is the qubit's quantum mechanical lifetime. If you start with a massive superposition state, let's assume we can create that perfectly in the quantum computer, you then start running your algorithm. That algorithm is a series of steps taking me from the initial state to what is the final state in the answer. And while I'm doing that, I'm not the only one controlling the qubits. The environment around the qubits is also interfering or controlling it. Electromagnetic fluctuations, temperature, vibrations, even cosmic rays, everything. They're so sensitive. And so over time, you can think of this state of the computer blurring and eventually disappearing. Now, the qubits didn't disappear, they're still there, but the point is I'm walking from point A to point B with my algorithm. Along the way, the environment is taking me to another state that is the wrong answer. And if I start again and do it, it's going to take me to a different wrong answer because it's stochastic, the noise. The time frame over which this happens is called the coherence time. The second time scale is the gate time. What's the time required for a single qubit operation? What does it take to do one step? And the figure of merit then, as you might imagine, is the ratio of these two. How many steps can I take before my quantum mechanical coherence goes away? Something to note here is that long coherence times is not sufficient on its own. We often hear technology platforms say, well, my coherence time is an hour. Oh yeah, well mine's a day. Well, that's great. What you really care about is you should ask that person, okay, but what's your gate time? Because what really matters is how many gates you can do. And it turns out that if you look at this metric, qubits platforms are basically in a dead heat at this point. So what I'm showing here on the left axis is this metric, left vertical axis, number of operations before an error. And on the right axis is what we in the jargon in the community would call gate fidelity. So if you have one error in 100 steps, that's 99% good. One in 1,000, 99.9% good, gate fidelity. And of course, higher fidelity is better. Now the horizontal axis is just gate speed. How rapidly can I take those steps? And that's the analog of the clock speed of our computers. So you want to be in the upper right corner. Leading platforms today, a trapped ion is one of them. You hold an ion in free space and you use the energy levels. They have very high single qubit fidelities. Those are the blue squares. They have pretty good 2 qubit fidelities. Those are the red triangles. But they're pretty slow. They're trying to make them faster. I work on superconducting qubits. We're already pretty fast, so we're improving our fidelities. And neutral atoms are up and coming. You can see how they fit in somewhere in between, silicon quantum dots. NV stands for nitrogen vacancy. That's a defect in diamond. There's defects in silicon. Many candidates here. This is what they look like. On the left, you see IBM's Osprey processor, Google's Willow processor. These are superconducting qubit processors. You can see that they're 3D integrated, heterogeneously integrated. And these are quite sophisticated systems at this point. In the upper middle is Quera's Aquila processor. Those are neutral atoms, if you see the little dot inside the magnet. Quantinuum's H1 is on the upper right. That is a trapped ion quantum computer, and you can see that it's built on a silicon chip, integrated photonics. Lower right is D-Wave, a different type of computing called quantum annealing. I won't talk about that today, but it's superconducting. And of course, in the bottom middle, that's obviously not a quantum computer. That is the Wright Flyer, as you may recognize. It's not the first time that humankind had flown. That's actually a misnomer. Before that, we had hot air balloons. We had aerodromes, unmanned aerodromes. But when we see the Wright Flyer, historically, we look back and we say, yeah, that's when it all came together. There's a person on board, self-propelled, took off, landed, and this was the dawn of commercial aviation, right? And I put this picture here because two reasons. One is that I think that our quantum computers today are about this level of sophistication, but also it is the dawn of commercial quantum computing. I think that we have seen enough and the system is complete enough, you can access a quantum computer online, write a program, and the answer comes back. The system is there. I wouldn't get on that plane, right? But I can look at it and say that, yeah, the system is there. So to realize then the promise of quantum computing, we have to engineer quantum systems that are robust, reproducible, and extensible, right? The way that we do that is through architecture. Of course, lots of technology improvements, but the architectural layers of a quantum processor look a lot like those of a conventional processor. You have the physical devices at the bottom, you have an application layer at the top, a logical controller to figure out what gates I need to apply to run my algorithm, interpret the program that I just input. And then you have two types of error suppression, passive and active. And I won't have time to go into the passive one today, but I will talk about the active one because it's so important. And on every clock cycle of a quantum computer, every time we take a step, we need to take the step in the algorithm, and then we need to check for errors. We take the next step, and we check for errors. We have to do that every clock cycle, and that's called active error correction. That is the grand challenge today. Our physical qubits have error rates of 1 in 100 to 1 in 1,000, 1 in 10,000, the yellow region that you see there. You could then ask, what do we actually need to achieve commercial success, right? Run something at a commercially large scale. That's the blue region, practical applications. You need to run 1 billion steps or even 1 trillion steps to be useful. There's a big chasm. By the way, CMOS is almost perfect. The error rate of CMOS is something like 1 in 10 to the 20 or better. Thankfully, we don't have to be that good. We'd take it if it were. But we do need to be in the blue region. And the way that we're going to overcome this giant chasm is through something called quantum error correction. And the concept, I think we're all familiar with. Rather than encoding the information in a single qubit, we're going to encode it into a team of qubits. Just like with people, we form teams of people, and if the individual people themselves are sufficiently performant, they cross some threshold, then grouping them together into a team, the team will outperform any of the individuals, right? My son is 16, but at one point in his life, he was 5 years old, and we would go to the playground, and there would be lots of kids playing on the playground, and it was heartwarming, but it was total chaos. Everybody's running all over the place. And if you added more kids to that playground, the chaos only increases, right? They are not yet beyond threshold to form a team. And our qubits 10, 15 years ago were all kindergartners, basically. But in the intervening 15 years, we've improved the qubits to a point where adding more qubits can actually improve performance. Okay. You could ask how much. Well, the logical error per cycle, that's the error of the team, has two parts. One is C, that's a cost. Forming a team is not free, right? You actually have to perform more gates, you have more people to take care of. There's an HR department, there's a security department, right? Like, it takes a lot to run a university. But you still do it because the win is, in fact, exponential, as you see here. And it's exponential in the size of the team, which in our jargon we call the distance. If your team is a 3x3 array, then that's distance 3. If it's a 5x5, it's distance 5. I didn't mention the blue qubits, I forgot. The blue qubits you can think of as referees. They're the ones that have a yellow card or a red card. In fact, there are 3 types of errors. There's a green card. They're going to flag when an error occurs, and I measure and look at the referee qubits to infer errors, but I never look at the data qubits. The data qubits hold the quantum information. If I measure those, it's game over. So instead, I measure the blue ones every clock cycle. So this is what it looks like. We've got the logical error on the vertical left axis and the physical error of the teammates on the horizontal axis. And you'll see that the logical error is on a log scale. Today, we're at about 1 error in 1,000 for the physical. And what you see is if I go from a distance 3 to a distance 5 code, I improve by a factor lambda. My error goes down. If I go 5 to 7, I'll go down by that same factor lambda. And I can just keep doing that. I just keep making the team bigger and bigger and bigger until I hit the logical error rate that I desire, something like 1 in a billion. I just stop there. I could keep going. So what did it cost me to gain that? Well, in this case, at D17, distance 17, I needed 577 qubits on my team, but I got an improvement down to 4 times 10 to the minus 9, an improvement of almost a factor 1 million, right? That's the promise of quantum error correction. This is what we're going to have to do to get into that blue region. Now, we still have work to do at universities. My group, we focus on improving the performance of individual qubits. And if I can improve the qubit by a factor 2, you can see at the logical level here it improves by more than a factor 10, right? That's also related to this exponential improvement. I bring this up because Google in 2025 published a paper which I think will be remembered. In a field with a lot of hype and breakthroughs every day, this one actually is a breakthrough. What you're seeing is the logical error is a function of the number of times that we run the error correction algorithm. And in red is distance 3, and then in teal is distance 5, and in dark blue is distance 7. We're adding more qubits. The logical qubit is getting bigger, but the error rate is going down. That's amazing, right? Conventional probability would not tell you that. If I have an error-prone system and I add more error-prone systems, it's just going to be faster to error. But here we've created a code where by adding more qubits, the error went down. And this is what we need to do if we're going to build large-scale quantum computers. So I'm at the end of the talk. I just want to mention this almost exactly a year ago at GTC, this gentleman here, Jensen Huang, you probably recognize him, CEO of NVIDIA. He was asked, when do you think we're going to have a quantum computer? As an engineer, I really respect Jensen, and he's smart, right? Very smart. And he said, well, look, if you said 15 years, that's probably on the early side. 30 years, it's probably a little late. 20 years. I think we'll have a quantum computer in 20 years. And for those who were following it, the stocks of the quantum computing companies all tanked. Because, oh my God, Jensen says it's going to be 20 years before we have a quantum computer. I actually was quite excited. I was like, Jensen said we're going to have a quantum computer in just 20 years. That's amazing, right? We started with the history of classical electronic computing, which arguably started more than 100 years ago. Now, 6 months after this, he realized, okay, what I said was, impacted those companies. And when he answered this question, he was thinking the quantum computer that's going to invent new pharmaceutical drugs. He was thinking the end game. But he qualified it. He said, look, technology doesn't evolve according to a step function that there's going to be nothing for 20 years and then suddenly we're going to have the end game quantum computer. That's not how it works. There will be improvements year by year by year by year, and eventually something commercial will be useful. If you used early classical computers in the 70s or 80s like I did, it was a very frustrating experience. It did something, but it never was quite enough. And the early quantum computers will be exactly like that. Right? Make no mistake. They're not going to be perfect, but they will be useful and they will be commercial. And so this is my last slide. If you think about technology readiness levels and maturity of quantum computing systems, I'd like us to just remember the TRL level of these two chips. The Intel 4004 in 1971, by today's standard, was pretty wimpy. But at that time, it was TRL 9. And of course, today we have Blackwell processor GPUs, right? And today, that would be TRL 9. And so if you ask me, and you can find it in this paper listed at the bottom, what is the TRL level of quantum computers today? I would say it's somewhere around 6 to 8, to be honest, because you can literally log into your computer terminal at home, program a quantum algorithm, send it to a company like IBM, get the answer back, and that's the whole system, right? Now, it needs to be much larger to be commercially powerful, but the system is there, just like this Intel 4004 processor did something, okay? So, a few things I'd just like to leave you with. Quantum computers are not going to replace classical computers. First off, they only solve certain tasks efficiently, not everything. And second of all, we need a classical computer next door to help us with the error correction. So they're always going to be run in tandem. We need more quantum algorithms. Please join hackathons. Help us develop tomorrow's commercial-grade quantum algorithms. We don't need to worry about encryption today. Shor's algorithm, when we have a quantum computer at scale, will compromise our current public key crypto system. But we do need to switch over to new crypto systems, classical ones, because we want to be forward secure. There is a notion of harvesting data today and storing it, and then when we have a quantum computer coming back and looking at that data at that time, right? So NIST has released its new standards for encryption, just classical algorithms, going by the name Crystal's Kyber and things like that. We need to switch over to that now so that we are also forward secure. And to realize the promise of quantum computing, we're almost certainly going to need error correction. And with that, conclude the talk, and I thank you for your attention.
Thank you very much. Should have microphones that can be shuttled around. So now is the time for questions. And then there's the awkward pause. And, okay, good. Right up front. Do I need the mic? Yeah, we'll get you the mic. Don't worry. It's just coming.
Yeah, thank you for a very nice talk and a very nice overview. I'm also from MIT, so I got all my degrees from there. Your talk seems to be predicated on the factor that we are using two superconducting qubit to make the next generation quantum computer. But from the history of technology, we know that cryogenics does not fly. We have the masers and the lasers, and then we have the transistor laser, and also the transistor laser versus the lasers that does not need cryogenics. Somebody was clever enough to remove cryogenics from semiconductor lasers. It seems that you have a system that needs lots of cryogenics, and it doesn't seem that the system will fly. Eventually, we would move away from that, in my opinion.
I completely agree, and I tried not to talk about my own research. I tried to be, fair across all the technologies. So what I talked about today is not solely about superconducting. It actually applies to all the different platforms. And you're absolutely right. Superconductors very likely will be the vacuum tube of conventional computing, but superconducting would be for quantum computing. They may be the first, but will they be the long-term winner? Okay, I don't have a crystal ball, but you're right. With cryogenics, probably not, to be honest, right? If we didn't have to cool them down to millikelvin temperatures, if we had an alternative that was just as good and didn't need the cryogenics, commercially we would switch to that. So superconducting qubits do require millikelvin temperatures. It's not a showstopper in any sense, but yeah, it's inconvenient. And when we have another technology platform that is as mature or more mature, it's likely that we would switch over. But today, I think superconducting qubits are in the lead.
We have a shy group.
What is the probability of using these quantum computers for nefarious reasons, such as like when you said crypto?
Yeah.
For the wallet keys.
Yeah.
Being able to decode that, would there be a probability of nefarious use?
Almost certainly. And that's why we really need to switch over to these new post-quantum crypto schemes that we believe are going to be immune to attack by quantum computers. Look, quantum computers don't solve every problem efficiently. And you could say that we just were unlucky in the 80s when we decided that RSA type encryption is going to be our public key crypto system. We picked that before we knew about quantum computers and later realized, quantum computer could actually break that crypto system. So over the last 10 years, researchers have come up with a new crypto system, just classical, based on lattice mathematics, which we believe is also hard for quantum computers to break. And so the task ahead of us is to switch over to that. And on the software side, it's already starting to happen. There's also a lot of embedded hardware that needs to change. So we're working on it. So there is a likelihood that quantum can be used for such a nefarious application, but we're not defenseless. There are things we can do to minimize its impact.
Thank you.
So we're going to do one last question because you may have noticed this is the in-between class time.
Yeah.
And the parade has started. So.
Thank you for the very nice presentation. So there have been concerns that quantum hardware has been marching at a regular pace, and people have been delivering what they promised in terms of reliability and a number of qubits. But on the other side, the software and the algorithms has been a bit behind.
Yeah.
Do you agree with that concern? Do you think that maybe we should be working also more on the at the same time on the software to?
Absolutely. Yeah, like I said, we need to develop more algorithms, and they need to be commercial grade, ideally, not just toy problems. It's very, very important to do this, right? Now, I think they go hand in hand, though, that there's some bootstrapping. It's very hard. Peter Shor is a genius, and he could, in the abstract, come up with an algorithm. But for me, I'm a mortal, right? And I actually need to try things and trial and error to come up with something new. And I think that with these quantum computers coming online, we will see a growth. Like, MIT has hackathons every year in quantum, and I know a number of places do around the world. This is exactly what we need to do, right? And to develop new algorithms. Most algorithms, I believe, are developed that way. Turbo codes, for example, in the early 90s. Nobody predicted that. It wasn't like we had a development of it. It was just people playing around with communication systems and signal processing and realized, oh, wow, look what we can do. So there is bootstrapping that's going to happen, and I think that will accelerate now that we have at least these small quantum computers available.
We have a small presentation.
Oh.
I think I'll ask you to stand over this way. Thank you.
Yeah, maybe I should. There we go.